does a person consume in a month? So I'm going to start with you four guys. How many sugar-containing drinks do you drink in a month? Juice, soda, whatever. Take a wild guess.
In a month.
Yeah. Yeah, if it's a whiskey sour, then it's got sugar in it. Does alcohol count?
Five.
What's that?
Five.
Five a month? That's all? Wow, that's pretty good.
No, 5 a week. No, 20.
Well, 5. Okay, 20. Okay, let's call it 20. Okay, you? 15. You can make this up. I'm not prying. If you don't want to tell me how many sugary drinks you drink. 35. Whoa. Okay, you're up with me. Actually, I drink the what do you call it? Fake sugary drinks. Yeah, and 30. Okay, that's good. I don't know if that's good, but okay. I'm gonna make up a few more numbers. So I have 9. I'm gonna say 20, 15, 30. How many do I have there? 5, 7. I'm gonna 10, and I'm gonna go back up towards the end here, and 30 again. Okay, so we've surveyed 9 people. Okay, now I want to know. I'm going to call you guys population of graduate students in public health, right? So I want to know what is the mean number of sugary drinks per month, consumption of sugary drinks per month for all public health students. Imagine that you were a random sample. Obviously, this was not a random sample, but imagine it was a random sample of 9 individual students that were taking graduate courses in public health. Okay, so now if I want to know what the average is of the population, well, I'll never know that unless I actually go into the population and ask everybody. So that's not feasible. So I'm going to take a sample. I have my sample is size 9. So my sample size is equal to 9. So that sample size is a mechanism for me to estimate the middle value, the average number of sugary drinks for someone that's within that population. So in order to find that average, I have to find the mean. Okay. Now, since it's a sample, I call the mean X bar. Okay, so a lot of ways I could skin a cat here. I could do this manually. I could add it up manually. I'm going to open up Excel just to make things go a little bit easier for me. Okay, there we go. And I'm going to blow this up. I'll reduce the window so I can fit it in here. And I'm going to copy these numbers in here. You might want to do the same thing. 20, because I'm using Excel right now. Okay, I want to do this manually first. 35, 30, 20, 15, 30, and 10. Okay, a lot of variability in there. Did I miss? I missed one, right? 15, 30, 10, another 30. Okay, quite a bit of variability in there. So if I want to find the average, I just find the mean, add them up, divide by 9. So the mean is equal to about 23. I call that X bar. Now, in order to have a judgment as to how variable that this population is, the standard deviation of the population, I can't, again, just like the mean, I'll never know it, what it really is. So the only clue that I have to it is the variability or the standard deviation of the sample. Just like the mean, I expect the standard deviation is going to approximate the standard deviation of the population. So standard deviation. Okay, so that's going to be equal to STDEV, parentheses, and the standard deviation is 8. Okay, so, I'm going to now look at this from the perspective of, well, that's very interesting. The mean that I get is 22. However, I want to know how precisely I know that mean, how reliable that estimate of the mean is. And I can tell right now, not going to be very reliable. In fact, you know what I'm going to do? Just to make things a little bit interesting, I'm going to make the variability a bit less. I'm changing some of these numbers. Maybe there's too many of them. 20, even a little less. Okay, where's another big number? Here's another big number. Okay, and 23, which is the furthest from 23, 30. Okay, there's variability is a little bit more under control there. So my mean is roughly 22 and a half sugary drinks per month that I believe represents the population. Okay, population mean is sigma, right? And I'm never going to know what sigma is, right? It's not something that's accessible to me. I'm sorry, population mean is mu. I'm never going to know what that's equal to. And population standard deviation is sigma. I'm not going to know what that's equal to either. But I'm going to use this and this as an estimate of what the population mean is, what the population standard deviation is. So if I want to estimate what level of confidence, I want to create a range within which I can have some level of confidence that I can measure, that I know, that will identify that the mean is between these two numbers. Okay, and we know, of course, we call that the confidence interval. So I'm going to create a confidence interval here. And the way that we would do it, if we knew the population mean and standard deviation, or if we had an estimate of population mean and we knew the population standard deviation, the way we would calculate it is we would say the mean, x bar, plus or minus 1.96, we'll discuss that in a second, times the standard error. Okay, so we'll discuss what that is also. I'm gonna add and subtract a number from the mean that I've calculated for my sample, and that number is going to include a measure of the probability of that's introduced by chance, our normal distribution. That's our 1.96. Where do we get that from? We get that from the z table, right? Because 1.96 represents negative 1.96 plus 1.96 represents 95% of the likely outcomes, right? So I want to be 95% certain I captured the actual population mean, so I'm going to use 1.96. What allows me to use 1.96 is the fact that I know, or I'm imagining I know, sigma. Okay, so now I'm going to multiply that by the measure of the variability. Now, the variability of the sample in the population is the standard deviation, or sigma. The variability of the sample means, x bar, for that sample size, is called the standard error. And the standard error is calculated by sigma over the square root of the sample size. Okay, so I need to know the sample size. Well, we know some measure of this. We don't know sigma, but we do know the sample size. And we do know the standard deviation of the sample. So I'm going to use the standard deviation of the sample in place of sigma. So I'm going to say that my confidence interval is going to be equal to x bar, right, plus or minus, and this is going to be my margin of error. It's going to be equal to some value. Now, I'm not going to put 1.96 in there. 1.96 is the z-score that I need on either side if I know the true standard deviation of the population. I don't know that, so I'm going to use something called t instead, a t-value instead, or a t-distribution instead. And then I'm going to multiply that by the standard error. Okay, so I'm going to do two things here. I'm going to calculate my standard error. Okay, my standard error is going to be equal to, oops, let me do that here. My standard error is going to be equal to my standard deviation, which is 5.87, divided by the square root of the sample size, which is 9. Okay, I'm going to hit return. And that's my standard error. The problem is that if I had known the population standard deviation, I would have a really good handle on what the standard error is. But by using the sample standard deviation instead of knowing the population standard deviation, I introduced another place where I have some uncertainty, right? Our standard deviation may not be accurately represent the population standard deviation. So because I have that extra layer of uncertainty, because I don't know the population standard deviation, I can't use the z-score anymore. I have to use something called the t-score, right? So the t-value is going to be a distribution like the Z distribution, with a, where you could have a table for it and everything, where that distribution is wider than the Z distribution, the normal distribution, to make up for that extra uncertainty. And the smaller the sample size, the wider that T distribution is. In other words, the bigger the T value I have to use for my 95% confidence interval. And where do we get that value from? Well, we can get it from Excel, we can get it from a table, and so on and so forth. So let's calculate what that T-score has to be for a 95% confidence interval. I'm going to look up my table. I think you have it in this week and last week on Blackboard. Okay, let's see, Agresti. These are from another textbook that we use often called Agresti and Franklin. Okay, so here's my T-table. Blow it up a little bit. Okay, so here's my 95% confidence interval. Notice underneath it says right tail probability 2.5%, 0.025. That's because when you, in this table, when they define the confidence interval, they're talking about the middle 95% of that distribution. So that means you have a 2.5% outside of 95% on the right end and 2.5% on the bottom end. They don't say anything about the left tail probability, but we know that they've considered it because they're using the t-value for right tail probability equals 0.0025 to represent the 95% confidence interval. In other words, you can see that would have to be doubled, right? So we're going to use this t-score in this column. So now my sample size determines what this t-score is going to be, right, for a 95% confidence interval. So I'm going to scroll down here, and I'm going to scroll down to the degrees of freedom. They don't use sample size, they use degrees of freedom, which is the sample size minus 1. So in our case, it's going to be 8 degrees of freedom. So the t-score I need to use instead of 1.96, the z-score, is 2.306. I'm just going to call it 2.3 for our purposes, because that's all I remember by the time I get back to the other page, right? Well, look at this. As the sample size gets bigger, what happens to the t-score? It gets smaller, right? Watch what happens if it gets really big. It becomes 1.96, just like your population. In fact, that's actually infinity. But once you get over a sample size of 100, it's so close that people forget about it and just use the z-score for really large samples, right? They will use 1.96 because, close, the law of close enough, right? So for our purposes, it's a small sample. So we're going to use 2.3, 8 degrees of freedom, 2.3. So I'm going to go back here, and now I'm going to say that's going to be 2.301, I think it was. I might as well put in that, right? So now I have everything I need to calculate my confidence interval. What is it going to be? It's going to be, the mean is 22.4. I'm going to round this stuff off. The standard error is one point. Coincidentally, it's 1.96. That's kind of, was that really what it is? I hate that. I don't like that. Okay, I'll leave it that way, but I hate that because I don't want to confuse you guys. 1.96. I'm going to call it 2. Right, I'm going to change this number to 2, just so we don't confuse it. The standard error happens to be 2. Right, standard errors happen to be 2. So this is x bar. This is our standard error. This is going to be our t-score is going to be 2.301. Right? So let's see what I can do now. So my confidence interval is going to be equal to the mean, 22.4, minus 2.03 times my standard error. Okay. Now, if I wanted to calculate this separately, let me do it separately for a second. If I want to calculate this separately, I could say my margin of error, my margin of error is equal to 2.03 times my standard error, right? That's my margin of error. So I could just copy that here. Oops, 4.602. I could just copy that there. And now what I can do is I can say to myself, well, the lower range is going to be equal to my mean minus my margin of error. And the upper limit is going to be equal to my mean plus my margin of error, right? So in other words, we're 95% sure the real true mean is between 17 and 18 and 27. We are 95% sure of this. Okay, now if I wanted to be 99% sure, if I wanted a 99% confidence interval, what would I change here? Bingo, the t-value. Everybody got that? Because I'm going to bring that t-table back up here. If I want to be 99% certain, I use the t-value that's in this column for 99% confidence interval. 8 degrees of freedom, I would have to use the number 3.5 instead of 2.3. If I go back here, you can see if I had used the number 3.5 instead of 2, right? I'm sorry, if I had used the number 3.5 instead of 2.3, that would have made my interval wider. I would have multiplied 3.5 times my standard error to get my margin of error. Bigger margin of error, you're adding and subtracting more from the mean, so it's going to be a wider number. Okay, so I'm going to give you an example for you guys to work out yourselves in a second. Okay, so now I'm going to say to myself, okay, that's great, that's terrific. But now what if I want to compare this to another group, right? To say the number of sugary drinks that is consumed by, instead of New York State public health students, California public health students. Well, what if I told you that California public health students, we surveyed all the students in California, and we found that the mean, mu, we know mu, California, and it happened to be equal to 20 sugary drinks. Now, I might ask you and say, well, gee, that's very interesting. Do you think that this proves that we drink more sugary drinks than they do? Keep in mind, this is our confidence interval, 95% confidence interval, right? The mean would suggest that we drink more sugary drinks, right? Their number, their mean, we know because we sampled everybody. We got everybody in the survey to answer that question. We know their mean. Our mean, we don't know. We think it's 22.4, but we don't know what certainty of that is. But we do have a range for our 95% level of certainty. We're 95% sure it's between 17 and 27. So do you think 20 is different than 22.4? Can I say that with any level of certainty? It would be kind of hard. Well, we're going to get to that in a second. Just looking at the confidence interval, you're 95% sure the true population mean for New York City, for New York students, is between 17 and 27, right? But now you got 20. It could very possibly be 20. That's inside that confidence range, right? It could be 20. We're certainly not 95% sure it's different than 20, right? So had it been 15, well, we're 95% sure it's not lower than 17, right? So maybe we're 95% sure that it is really lower in California. Now, there's reasons why we don't use the confidence interval this way. We use the confidence interval strictly to estimate our probability of capturing the mean with a certain couple of numbers. We use a t-test, which is very similar, right? Works very similar, but the mechanism for it is a little bit different. It'll become more different when we're using multiple samples. See, in this case, we're only using one sample, right? We're only using, the only sample here is the one that we took in New York. The California mean, we know because it's not a sample. We know it to be a fact. That's the mean for California. So when we do a t-test, this test using this t-value, to compare California to New York, we're going to be doing a single sample t-test. We're going to be taking our sample values and comparing them to a known value somewhere else. Okay, and the way that we're going to do this is we're going to actually calculate a t-value for the difference between these two values. And the t-value kind of represents, remember in the z-score we were talking about when that we described the z-score as kind of being the number of standard deviations that two values are apart. Like if the mean was 100 and the standard deviation was 10, then a value of 80 would be two standard deviations below the mean, or a z-score of 2, -2. Or a value of 120 would be a z-score of +2, right? Two standard deviations above the mean. The t-score is kind of the same thing, except the t-score is using the t-distribution for that sample size, for that specific sample size, so that if I told you we had a sample and the sample was size 9, well, now when you looked at two standard deviations, it wouldn't be quite as far down away as it would be for the z-score. Okay, it'll make some more sense to you when I actually do this calculation. So I'm going to take these values that we just worked with, and I'm going to copy them into SPSS. I'm going to open SPSS up. It'll bounce for a while, and then eventually start, I hope. Yes.
You missed the top one.
Did I? Oh, did I? Okay, I'll try that again. Oops. See, now I'm copying and pasting. Oh, it stays clear. That's right. It actually did copied it. There's a number of ways that I could have done this. Right, this is just one of them. So I'm just going to take this. I'm going to click in here, and I'm going to say paste. Okay, and there's my numbers. There's the 9 numbers. You could type them in if you wanted to, and so on. So there's my 9 numbers represented there. Unfortunately, SPSS doesn't follow the rules, so I can't expand this window. I can't blow up this window. So it doesn't give me a chance to do that. Okay, so now I want to calculate the same statistics that I did before. So I'm going to go over here to Analyze. And then I'm going to go down to Descriptive Statistics, right? Mean, standard deviation. Those are the kind of values that we calculate for numerical values, okay? And that's a descriptive statistics. First thing I see in descriptive statistics is frequencies. Frequencies is just a count. It's just going to count the number of values that are identified as that group. For instance, it could be the number of people that are diabetic versus the number of people not diabetic. It could be different hair colors. Could be different nationalities, right? Those are nominal values. Nominal values. They're not, or you want to describe them categories or names, nominal or categorical values. Those you count stuff. When we talk about numerical values like this number of drinks and so on and so forth, that's a numerical value. We're not going to do frequencies because frequencies is just going to give us a list of the numbers again. Right? We're going to go into descriptives instead. Okay, so descriptives has pretty simple. It just has a chance for you to just move that one variable that you created into the work page. In other words, SPSS opens this window. It shows you all the variables that are available. Well, there is that one that I pasted in. And I'm going to move that into this other column to let it know I'm going to work with that variable. Notice it gave it its own variable name because I didn't give it one. So I'm going to click Options. Right? And I'm going to look at what's going to calculate. Right now, it's going to calculate the mean, the standard deviation, the variance, range. I'm going to click a few other things on. And I'm going to say OK, and then say OK, go ahead and do the calculation. OK, so here's what it calculates. Well, the range is 20. It's from 10 to 30. The mean is 22.44. Same thing we got. The standard deviation is 5.87, the same as we got when we did our calculation by hand or by Excel. And the variance is just a square. You remember the variance is just the square of the standard deviation, or vice versa, the standard deviation is the square root of the variance, right? Well, that's not quite what I wanted, right? Now I would have to look up my t-score. I would have to figure out what my standard error is based on the sample size and degrees of freedom. It really didn't do the whole thing for me. So I'm going to go back up here to Analyze, Descriptive Statistics, and I'm going to go past Descriptives and go to Explore. That's going to work with Descriptive Statistics, except it's going to give us more options. So in this case, I'm going to move the variable into the top box. That's our work box. These are others. We'll figure that out later. I'm going to click on Statistics. And it already knows, it already has a laundry list of statistics that it's going to do. But one of the things that it's going to calculate is the confidence interval for us for the mean on those based on those numbers, just as we did it manually now. Now, I'm not always going to want a 95% confidence interval. I may occasionally want a 90% confidence interval or a 99% confidence interval. So I could change that here if I wanted to. I'm not going to do that right now. I'm going to leave it 95%. Okay, I could ask it to do percentiles. I could, and a few other things. Okay, I'll leave that turned on. So I'm going to click Continue. And then I'm going to click OK, and it'll do the calculation. Actually, I can also ask it to do plots and so on and so forth. In fact, it always does a box plot for you automatically. Okay, so I'm going to click OK. Let's see what happens this time. Well, now I get I just call it a laundry list. It really is a laundry list of results here, right? So let's see what it told me. It told me that the mean is 22.444. Oh, look, this time, in addition to the standard deviation, 5.87, it calculated the standard error, which is, remember I changed that to a 2 to keep it from getting confusing, but it got the same number we did. Now, it took that standard error and it multiplied it by the t-score, right? It took the standard error, multiplied it by the t-score, added it to the mean, and subtracted it from the mean, and it got the 17.927 to the 26.96. The same thing we got. Actually, it's a little bit different because I remember I changed it to 2, right? So it did the same operation we did with a lot less stress and work, right? Now, there's only 9 numbers here, right? You can imagine it would have been tougher for us if we had a sample size of 223, right? So that's one of the big advantages of SPSS, is it's going to save you a lot of money in the long term, right? It does a few other. Here's the box plot that it created. 30 is the highest number, 20 is the lowest. The median is around 24 or something like that. Okay, so, and there's percentiles, there's a few other things. But really, the important thing here is it did this calculation for confidence interval for us. Well, now we're going to take it another step further. I'm going to take this same sample that we took, and I'm going to go into Analyze, except this time I'm going to do the first real statistical test that we're doing in this class. I'm going to take that example I just gave you to see whether or not this data will tell me what level of certainty I have that this data will tell me that what we measured here in New York with our sample is enough to tell us that we can say that there's a difference in the number of sugary drink consumption in California and New York, right? So the way I'm going to do that is I'm going to compare means. I'm going to compare the mean from our sample to the known mean from California. So I'm going to go compare means, and I'm going to go in here. It's a one sample t-test. Remember why I said it was one sample? California, we know the mean. New York, we don't, so we had to do it from a sample. So we're comparing one sample to a known value. So I'm going to click on that. It's going to come up. It's going to ask me what variable. Remember, I could have many variables in my data set. Age, BMI, number of sugary drinks. I have to tell it which one I want to work with. So I'm going to move in the variable that this happens to have only one variable. And now I'm going to put in the number or the mean that I'm comparing it to. Guys, remember, what did I say it was going to be? 20? 20. I'm going to compare it to 20. Okay. Now SPSS is going to say to itself, well, gee, now I'm going to look at the mean, and I'm going to look at the mean for California. I'm going to look at the mean for New York, and I'm going to find the difference between the two of them. I'm going to subtract X bar from mu, X bar minus mu. And I'm going to divide that by, well, let's see, the number of standard deviations or standard errors apart that they are. My t-value, that involves my sample size and t-value. So I'm going to say, okay, and it's going to do that calculation for me. So what did it do? And I'm going to do this manually in a second. So what did it do? It said, okay, the t-value, the number of standard deviations apart, standard errors apart that these two means are, is 1.25 roughly, right? Now, what did we need? What did our t-value, what t-value did we use to have a 95% level of confidence that we knew where the mean was? For a sample size of 9. You remember what that t-value had to be? 2.3, right? So we need to know if these two values are at least that far apart in the t-value to say with 95% certainty that they're really different, right? So do I have a t-value that big? No, I don't, right? And next, so if I did have a t-value that big, what would it tell me? It would tell me I'm 95% sure that these two means are different, right? So what's the chances that I would be wrong by saying that? If I'm 95% sure it's right, what's my chances of being wrong? 5%. This little thing over here called significance is also called a p-value in your textbook, in most textbook. SPSS calls it significance two-tailed, right? That's a p-value. This is the probability of being wrong if you say that the two means are the same. Two means are different. That's 24. That's almost 25%. If we want to be 95% certain we're right, that means we want to be less than 5% chance of being wrong. So we need this t-value to be more than 2.3. We have a name for that. We call that a critical value of t. And we need our significance level to be less than 0.05 in order for the same reason. Okay, so this has to be more than 2.3. This has to be less than 0.05. Okay, in fact, you don't need to go to the table, because if this is less than 0.05, you know you're already going to have a t-value, which is big enough. Okay, let's go back to our numbers and do this calculation. Okay, let me get Excel back up. Oops, where'd it go? Okay, so I'm going to scroll this up a little bit. Okay, so let's see the two numbers we're calculating. Okay, let's see, x bar minus mu, the known value of that other population, over, what is it, over the standard error. It's going to tell me how many standard errors apart that these two things are. So that's going to be equal to, it's going to be equal to 22.4 minus 20. I'm going to put 20 in here. Excuse me. Divided by the standard error. Standard error was, I called it 2 to round it off. I got to put this into parentheses so it does that first before it does the calculation, and it comes up to 1.2. You guys remember what the t-score was before at SPSS? It was roughly 1.2. That's how the t-score is calculated, right? Now, if my sample size had been larger, my standard error would be smaller because you divide by the square root of the sample size. So t would have been bigger. So I'm going to do another comparison. Okay, that comparison is going to be, let's see if it's different than 15. Let's say I did Utah. Utah, they drink 15 sugary drinks, right? So what that's going to be equal to is going to be equal to 15. X bar is ours, is 22.4 minus 15 divided by the number of standard errors, which is, where's the standard error? Which is, I called it 2, I rounded it off. So let's see what my t-score is now. T-score is 3.7 now. What do you think about that 3.7? What t-value do we need for to be 95% certain for a sample size of 9? Remember what the t-value had to be? It had to be 2.3. So have we exceeded that critical value? 3.7. We have exceeded it. So now I know with 95% certainty that these two means are different from one another. Also, even more accurately, with less than 5% chance of being wrong. Okay. So let me go back to SPSS and do that same test with 15. Keep in mind, numbers are going to be a little bit different because I took the liberty of rounding that to 2 in Excel. Descriptive Statistics, Explore, and now this time, I'm sorry, Analyze Descriptive Statistics, Compare Means, one sample t-test, and this time I'm going to compare it to a known mean in Utah of 15. I'm going to click OK, and this time my t-score comes out to be 3.8. I don't remember what I just calculated, but it was somewhere in that vicinity. My degrees of freedom is 8, we know that, and our significance is 0.005. Is it less than 0.05 now? Yeah, it is. So now I can say with less than 5% chance of being wrong that the mean for sugary drink consumption in Utah is different from the sugary drink consumption in New York. Okay, so now I'm going to formalize this whole thing. We're going to do something called a hypothesis test. Okay, we have a way of describing the type of errors that you can have when you do statistical analyses. Okay, and we describe them as type 1 and type 2 errors. We also call them alpha and beta errors in another context, right? So I'm going to describe them as alpha and beta errors. Okay. Before I do that, I'm going to talk about this idea of hypothesis test. Okay, so now I want to prove that the mean of I'm going to pick another state, Texas. I'm going to say I want to prove that the mean consumption of sugary drinks in Texas is different than the mean in New York City. Okay, I know the mean for Texas. I use New York City. I take a sample of New York City to get that mean, just as we've done. Okay, so now I'm going to start out, instead of saying, one way for me to say that is to say the mean in Texas is not equal to the mean in New York. Okay? That's literally what I'm saying here. That's what I want to prove, right? The mean in Texas is not equal to the mean in New York. Well, you know what I'm going to do? Instead of starting with that, I'm going to go back a step. I'm going to say to myself, let's say that that's not true, and now force myself to prove it. So I'm going to start with the mean in Texas is equal to the mean in New York. Okay, I'm going to start with that instead of the not equal to. What do you think we call? Anybody know what we call this hypothesis? That they're equal?
No.
You've heard? Have you? No, not yet. That's called a null hypothesis. Null means no difference. Null, zero or no difference. Null hypothesis. Sometimes they'll abbreviate H with a zero. That's the null hypothesis. Okay, that's the null hypothesis. What do you think we might call that other one? I'm going to call that one the alternative hypothesis. It's not equal to. Not equal to is the alternative hypothesis. I'm going to start with the null hypothesis. My starting point. Null is that null means no difference, right? Null hypothesis is that they're equal to each other. Okay? My alternative, it seems a little bit weird, right? Null sometimes uses zero or something like that. The null hypothesis is that they're equal to each other. There's no difference between them. The alternative hypothesis is that there is a difference, that they're not equal to. And the way I write that usually is mu of group 1 is equal to mu of group 2, right? So in this case, really, since we know what Texas is, I'm going to call Texas 17. I'm going to call Texas 18.5. I'm going to say mu is equal to 18.5. So really what we're saying is that 18.5 is equal to New York City. And the alternative is 18.5 is not equal to New York City. Okay, now I want to be 95% sure of this before I shoot my mouth off about this. In other words, I want less than 5% chance of being wrong. That kind of error, where we say that there's a difference when there isn't, we call that an alpha error. Right? So alpha error. We want our alpha error to be less than 0.05. We want our alpha error to be less than 0.05. Okay. So there's something called beta error, and then there's something called power, and we're going to get into that as we move forward. But I want our alpha error to be less than 0.05. So in other words, the key here is I want less than 5% chance of being wrong if I say that they're not equal, but forgetting about the fact that they're equal, reject the null hypothesis and accept the alternative hypothesis. I don't want that. I don't want to say that unless I'm at least 95% sure. Less than 5% chance of being wrong. Okay, so now, in order to do this, I have to figure out how many standard errors apart the difference is between these two. So I'm going to say my t-score is going to be equal to the sample, x bar, minus the mean that's known over the standard error. Okay. Now we calculated our mean and standard error before, right? Our mean was 22.4 and our standard error was 2. It's really 1.95, I think. I'm going to use 1.95 this time. Okay, our mean, so what is t equal to? T is equal to 22.4 minus 18.5. I should have done it the other way around, right? It doesn't really matter. I'm just going to wind up with a negative, with the z-score and the t-score, it doesn't matter, positive or negative, but that's okay. The difference is 22.4 minus 18.5 divided by my standard error, which was, my standard error was 1.95. I'm doing a little bit more accurately. Okay, so let's do that calculation. Are these two numbers more than 2.3 standard deviations apart? Remember, t critical is equal to 2.3. And that's the same thing as saying less than 0.05 on my probability of being wrong. Okay, if I exceed that number, I have less than 0.05% chance of being wrong. So let's calculate that out. (22.4) minus 18.5 divided by 1.95. Okay, what's my t-score? My t-score is equal to 2.0. Okay, can I reject my null hypothesis? Have I exceeded the critical value of t? Are they enough standard deviations apart? What was the critical value? 2.3. Have I exceeded it? No. Can I reject my null hypothesis? No, you can't. So I have to say that I fail to reject my null hypothesis. You can't say anything about your alternative hypothesis because you don't know anything. All you know is you didn't have enough evidence to reject the null hypothesis that the two means are equal to one another.
You won't be less than 0.5.
Let's give it a try. That's a good point. Let's give it a try right now in SPSS. I'm going to compare it to 18.5 now. Okay, let's go back to our output window. I'm going to go to Analyze, Compare Means, One Sample T-Test. Except this time I'm going to change this to 18.5. 18.5. And I'm going to click OK. Let's see what we come up with. Our t-value is 2.014. I'm doing some rounding, remember. So it's 2. Our degrees of freedom is 8. What is our significance or p-value? It's 0.079. It's bigger than 0.05. That means my chances of being wrong, if I reject the null hypothesis, my alpha error, is 7.9%. I can only accept a 5% chance of being wrong. This is how most studies work. Most studies, you publish, and your level of the point at which you say that you have a statistically significant result is usually when you have less than 5% chance of being wrong. Well, what does that tell you about most studies? If all the studies were accepted that you could have 5% chance of being wrong, what does that tell you about studies? That tells you that, gee, 1 out of 20 studies could just be completely wrong, right? And that happens, right? You read these studies, oh, well, like saccharin gives mice cancer, then somebody else does a study, can't replicate it. So it does happen occasionally, right? So the smaller the significance, the bigger the t-value, the bigger the difference between the two means, your sample mean, what you're comparing it to, the more likely you are, the bigger your t-value is going to be, the smaller your p-value is going to be, the less likely you're going to make a mistake. That p-value is the probability of making a mistake, and the key in most studies is to be less than 0.05. Right? So that's what this is all about. Now imagine, what does this tool give us now? This tool gives us a whole new thing that we can do. Right now, we're only capable of using this in a situation where we take a sample and compare it to a known value. Doesn't happen that often. More often than not, if we want to compare the cholesterol levels of people who eat a Mediterranean diet to people who eat an American diet, I'm not going to sample everybody's cholesterol that eats these two diets. I'm going to say take 50 people that eat this kind of diet, 50 people that eat this kind of diet, randomly sample them, and from some fixed population, randomly sample them, try and control for other factors, randomly sample them, get the mean of this group, the mean of this group, and compare the two of them. Now, that's a little bit more complicated, isn't it? Now we don't have a known value in one sample. Now we have two means from two samples. Well, if I go up here to Analyze, Compare Means, what do we get next? Independent Samples T-Tests. We can do that in SPSS. Just as we did it here, we can do it there. The difference is is that when we calculate the standard error, the sample size, there's two samples now. They could be the same size sample. They could be different size samples. They could be, one group could have a standard deviation which is very different from the other group, or the two standard deviations could be very similar. If they're very similar, you might want to combine the two standard deviations, combine all the numbers into one group for the two standard deviations so that you get a better estimate of the two standard deviations, especially if you think there's only a difference in the mean, not in the variability of the two populations, right? So there's all sorts of complications that come up from that point. But the basis is the same thing that we're doing here. You're going to look at the difference between mean 1 and mean 2. Instead of mean 1 and mu, it's mean 1 and x bar 1 and x bar 2. You look at the difference, then calculate a single standard error for those two groups, one way or another, either equal variances, unequal variances, and divide by that to see how many standard errors apart they are, and then based on the sample size, decide what your critical value of t has to be. Or use SPSS to decide it for you and give you the p-value right away. So now we're 1 week away from being able to do real control studies for drug tests, for interventions where, like, you might educate diabetics on diet, and then take a group that you didn't educate and a group that you did educate and compare their blood sugars or something like that. We're like a week away of literally doing real statistics here that people would use to publish articles and stuff like that. Okay, that's pretty cool, right?
Yeah.
Okay, so I'm going to put up a homework, which is going to give you some examples of this. I'll give you, like, for starters, I'm going to stick with a single sample t-test, right? And you can do it by hand, by Excel, using Excel, or using SPSS, or all three. Just so you know, if you work with Excel, for instance, just to show you, here we go. Just so you know that this is conceivable. If you type your data into Excel, I'm going to clear out all this stuff here. And all this junk that's down here. So all I got left is the data. Okay, and I'm going to go in here. I'm going to put an extra line in here. At the top of this, I'm going to say sugary drinks. Okay, notice I didn't put any spaces in there. I started with a letter. I didn't put any odd characters, stars, asterisks, underscores, anything like that. I could use letters and numbers, start with a letter, no spaces, no weird characters. Okay, I'm going to save this to my desktop. Save as, and I'm going to call it drinks. And it's up there with 1,000 other things on my desktop. Doesn't look that much different than my real desktop, unfortunately. Okay, I'm going to go to SPSS, and I'm going to say from SPSS, from File, I'm going to say I want to open an existing database, open. And I'm going to go over here to Open Data. Okay, it's going to open up a window. It's in Documents, so I got to navigate to my user area and then go into my desktop. Might be different for you guys on PCs. I don't see the file here right now because it only looks for its own files, .sav files. You have to click in here and tell it to look for Excel files, right? So now I can see there's some Excel files in here, including the one I just created, drinks.xls. I'm going to click on that and say open, and it's going to open it it's going to take the information in Excel, bring it into SPSS. First thing it does, opens a window that says, listen, do you want me to read the variable name from the first row of data? I put the name in there at the top. If I didn't put that in there at the top, I need to uncheck that, because otherwise it would ignore that number and use it for the variable name instead of actually seeing it as data. In this case, I need to do this, otherwise it would think that that word is part of the data, right? So you got to tell it is the variable name at the top of that column. Yes, and if you look at the description, it says on worksheet 1, there's data between cell A1 and A10. Makes sense, right? That A1 is the name, and then the other 9 numbers are the actual data. I'm going to click OK, and it'll open up, and there it is to copy the data into Excel. If I want, I can go into the variable view, And in the variable view, I can, sugary drinks, I can go into the label and make it a little bit more descriptive. Sugary, sugary drinks per month. So now, whenever it does a table or something like that, rather than use that thing with no space, might be abbreviated, look weird, it'll use a label description on the tables and graphs and so on and so forth. Okay, and then you can also alter some other stuff. I won't go into that right now.